Thanks for attending our EcoFest virtual booth. In this video, we'll be discussing the Commission's ongoing regional chloride study. In this study, we are evaluating sources, concentrations, and management practices for chloride pollution to our region's surface waters. By the end of this video, we hope that you'll understand why chloride can be harmful to our environment, how we're studying chloride in our surface waters, and how we can better manage chloride to maintain public safety while protecting our lakes, streams, and rivers. So what is chloride and why should we care about it? Chloride is naturally occurring as halite, also known as rock salt, which is shown in the upper right picture. It is a main component of table salt, also known as sodium chloride. Chloride is an essential electrolyte that helps maintain water and pH balance in our bodies. It is a negatively charged ion that is soluble in water, making it highly immobile in our environment. It's also relatively non-reactive, with no natural processes that remove chloride from our surface waters. And while chloride is essential to human health at low concentrations, it can be problematic for humans and other organisms at high concentrations. There are many sources of chloride to the environment, including natural and man-made sources. Natural sources include atmospheric deposition and weathering of minerals in soil and rocks. Man-made sources include winter de-icing and road salt application, water softeners, wastewater treatment, chemical manufacturing and food processing, potassium chloride fertilizer, animal waste and feedlots, and leachate from landfills. These man-made sources generally contribute to higher chloride concentrations in our environment that can be toxic for aquatic organisms. In recognition of the toxic effects of chloride, the Wisconsin Department of Natural Resources and Environmental Protection Agency have set chronic and acute toxicity standards for chloride in surface waters, which is shown in the table at the top of the slide. The EPA also has an additional drinking water standard for chloride at 230 milligrams per liter, which is when water begins to taste salty. At this concentration, it only takes 1 teaspoon of chloride to pollute 5 gallons of water. To put these toxicity standards in context, the chloride concentrations of our surface waters before European settlement was likely less than 5 milligrams per liter. One of the major man-made sources of chloride to our surface waters is through road salt application. Use of road salt in the United States has been increasing over time, as shown in this graph on the left of the slide. Road salt application really began ramping up in the 1960s with the expansion of the US highway system and more widespread use of personal vehicles. Over time, we have become accustomed to heavily salting our roads to keep them dry and clear in winter, even following large winter storms. Similarly, sometimes business owners have contractors heavily apply salt to parking lots to keep them snow-free and avoid issues with liability. All of this road salt eventually washes into our streams, rivers, and lakes. The Commission has embarked on a 6-year study to evaluate sources, concentrations, and impacts of chloride in our environment, as well as to develop management recommendations that minimize environmental damage while meeting public safety objectives. We are currently completing our 2-year field data collection effort and beginning our 4-year data analysis effort. Our goals are to estimate chloride loads from all sources, review state-of-the-art technology and best management practices, and recommend solutions that protect us and our environment. In this study, we have established 40 monitoring sites on streams and rivers across our 7-county region. You can see a map of our sites on the right of the slide. Pictures of an example site are at the bottom of the slide, with a sensor collecting data in the water and a telemetry unit sending that data to a cloud server. At each of these sites, we've been continuously monitoring specific conductance, water temperatures, and water levels every 5 minutes since October 1st, 2018. That's over 10 million observations combined. In another video linked in our virtual booth, you can join in on a field visit to one of our monitoring sites. Nick and Alexis will take you through our sampling procedures and demonstrate what the equipment looks like and how it is used. In addition to the continuous monitoring, we're also collecting stream and river grab samples at each site every month, as well as event sampling during snowstorms and snowmelt events when chloride concentrations tend to spike. These samples are analyzed for their concentrations of chloride, sulfate, potassium, magnesium, and sodium, as well as water hardness. We're also using a sonde to measure the specific conductance of the water during these visits to ensure that our continuous sensors are collecting accurate data. As Alexis and Nick demonstrate in our field video, we'll be using our continuous conductivity data as a proxy for surface water chloride concentrations based on a regression model that we're developing as part of this study. This graph presents some preliminary chloride and conductivity results from the Root River at Hoare Lake Dam in Racine. The blue line is the continuous specific conductance, and the black triangles are the laboratory analyzed chloride concentrations from the Root River. The orange dashed line is the DNR's chronic toxicity criterion of 395 milligrams per liter. Long-term exposure to these chloride levels is harmful to aquatic life. The red dashed line is the acute chloride toxicity criterion. 24 hours exposure to these levels can be toxic to aquatic organisms. The date is on the x-axis at the bottom of the graph, while the left y-axis is specific conductance, and the right y-axis is chloride concentration. While this site is generally below chronic toxicity levels, it does occasionally see these levels during winter spike events, as seen during February 2020 and February 2021. These winter spikes are characteristic of our more urban sites, where de-icing salts are applied to impervious surfaces like roads and parking lots, and then are rapidly flushed into our surface waters with snow and ice melt. This graph shows the range of observed chloride concentrations at sites along the Des Plaines, Root River, Pike River, and Oak Creek using box plots. The horizontal x-axis lists the site name, while the vertical y-axis displays the chloride concentrations. The orange dashed line is the chronic chloride toxicity criterion, while the red dashed line is the acute chloride toxicity criterion. The site with the highest average chloride concentration is Oak Creek, an urban site, while the Root River Canal, more of a rural site, has the lowest average chloride in these example stream sites. While each of the sites is usually below the chronic toxicity level, all of these sites, except for the Root River Canal, have exceeded these levels during winter spike events. Oak Creek even exceeds the acute toxicity level during these winter spike events. To help explain the chloride and conductivity trends we're observing at each site, we are interested in looking at the characteristics of their respective drainage areas. You can see the drainage area and land use for the Root River at Hoare Lake Dam site in the map on the right. For each site, we delineated the drainage area so we can look at the geology and soils, which could influence our conductivity chloride relationship. We also want to look at the land use, particularly differences in chloride sources and concentrations between urban and rural sites. We also want to look at the presence or absence of wastewater treatment facilities upstream of the site, which may be inputting chloride from home water softening systems. The next step in our study is to finish up our field data collection, and we're currently completing our final winter sampling at targeted sites across the region. We'll continue to collect information on chloride sources to our environment, including amounts of road salt and de-icing used by municipalities in southeastern Wisconsin. We'll also continue to gather information on some of the innovative techniques our communities have been using to reduce chloride application, including pre-treating roads with brine before winter storms, outfitting snowplows with temperature sensors, and replacing older water softeners with more updated and efficient versions. In closing, we'd like to thank our funding sources and partners as listed on this slide. If you're interested in our study and would like more information, you can contact our Chief Environmental Engineer or our Chief Biologist at their contacts below, or you can read more about the study on our website. Thanks for listening and enjoy the rest of EcoFest.